This is an overview lesson of the notes on covalent and molecular bonding, polarity, and intermolecular forces. We've talked a lot about chemical bonds so far. We know how to draw them. We've drawn ionic bonding, the transfer of electrons. We've drawn covalent bonding, where they're sharing electrons. We've talked about the properties of the different types of chemical bonds and what those compounds are like. So some of the things in these notes are going to be review, especially this very first slide. We already know from formula writing that covalent compounds have nonmetals in them, nonmetals attracted to other nonmetals. We know that they're sharing electrons in a covalent bond. With ionic compounds, that force of attraction in that chemical bond is so strong with the electrostatic attractions, the positive and negative charges, that all ionic compounds at room temperature exist as solids because the force of attraction in an ionic bond is so strong. Covalent bonds are still strong bonds, but they're a little bit weaker because of the fact that they're sharing electrons. So for covalent compounds at room temperature, we might see a covalent compound that is a solid. We might find one that's a liquid or one that's a gas because those bonds are not as strong as the ionic attractions in ionic compounds. You do need to highlight or put a star by those special 7 diatomic molecules. I use the phrase Brinkelhoff to help remember those special 7 that when they're in elemental form, they are always attached in pairs. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are all diatomic molecules, and they are all covalently bonded as elements because they are all nonmetals. We do want to talk a lot about polarity. We'll get into more details as far as what makes a bond polar versus a molecule polar, but just as an overview of what it means for a molecule to be polar itself, polar does mean that one side of that molecule has a slight positive charge and the other side has a slight negative charge, and there are reasons for that. Like I said, we'll get into details of really explaining how you know when something is polar. But I like this picture a lot because it helps represent as a visual what a polar molecule looks like. What you're seeing here are the nuclei of 2 atoms that are covalently bonded, so they're sharing electrons. If you'll notice that the nucleus of the atom on the right is larger, more protons are in that nucleus, and as a result there's a stronger pull from that nucleus on the electrons, not only its own electrons, but the electrons in the bond between these 2 atoms. The nucleus on the left is much smaller. It doesn't have as many protons, so its nuclear pull is not as great. If you'll also notice the gray shaded part representing the electron cloud is being shifted towards that stronger nucleus because that nucleus has a greater pull. We've used the term electronegativity before. That is referring to the pull an atom has for shared electrons in a covalent bond. So that's kind of what you're seeing here, is the more electronegative atom on the right is pulling the electrons more to its side. As a result, that side of the molecule will have a slight negative charge to it. Okay, the other side of the molecule, because the electrons are being pulled away from that side, has a slight positive charge. And those charges are permanent. So it's like a magnet, and it makes this molecule, which is polar because it has one pole that's negative and one pole that's positive, very attracted to things that are like it because of those opposite charge attractions. So it wants to be attracted to other polar things. These are permanent charges, so it'll stay like a little permanent magnet. Polar molecules are also called dipoles because they have 2 different charged poles. So I like this visual for polar. This section goes into a little more detail too about how you know a polar bond versus a polar molecule. And again, we'll go into the really details of that on a separate activity at the end of these notes. But this just kind of talks about the difference in a polar molecule versus a polar bond. Polar bonds have unequal sharing of electrons because you have an atom that's more electronegative than the other one. All right. We have talked about chemical bonds at this point, and those are intramolecular forces. I don't like the word intramolecular force because it sounds too much like intermolecular force. So I will use the word chemical bond when I'm talking about an intramolecular force. That is ionic and covalent bonds. Those are strong forces of attraction, and they determine what the substance is. So in the diagram, you can see there's a covalent bond pictured because it's sharing electrons between two nonmetals, hydrogen and chlorine. Okay, if I break the covalent bond that's there, that takes energy to do it, but also I would end up having new substances. I'd have hydrogen gas and chlorine gas rather than the compound hydrogen chloride. So that's a chemical change when I break the chemical bond. The force of attraction we're focusing on more today is an intermolecular force. Inter means between. And then the other part of that word is molecule. So between the molecules is what we're looking at. This is an intermolecular force. That force of attraction, if I were to strengthen it or weaken it, would only determine the state of matter of these covalent compounds. So this is only going to be in covalent compounds, molecular compounds, because in ionic compounds, the force of attraction is that strong opposite charge. Well, in covalent compounds, when we have polarity, then there's different forces of attraction that hold one molecule to another one. And that's where this word intermolecular force comes from. So chemical bond determines what the substance is. Intermolecular forces determine the state of matter. So that's the difference in what we're talking about. And now that we understand a little bit about polarity, and we're going to understand even more in just a little bit, we can understand how these forces of attraction called intermolecular forces work. Okay, so like I said, this slide is just telling us that intermolecular forces determine state of matter, physical properties, like solid, liquid, gas, okay, evaporating points, melting points, boiling points. So IMFs, or intermolecular forces, are tied to states. There are two main types that we're going to talk about today. The first one is an intermolecular force that occurs in all covalent compounds. All covalently bonded compounds are attracted to another compound just like it by at least something called dispersion forces. And that's the term that we're going to use. Induced dipole is another word for this, but we use the word dispersion forces. It's much easier. Dispersion forces are just the weakest type of intermolecular force, and it's a result of these molecules having electrons. Anything that has electrons in it, atoms, molecules, those electrons are constantly moving around. So sometimes there's a little bit of a backup, a traffic jam that can occur, and it causes temporary flashes along that molecule of negative or positive. If there's enough of those going on in enough molecules, it can be the result, or what results is a weak attraction to another molecule. All molecules have this type of intermolecular force. Okay, so any molecule, whether it's polar or nonpolar, will have this type force of attraction. A second, stronger intermolecular force only happens with dipole molecules, or with polar molecules. It's called a dipole force. So a molecule has to be polar in order to experience this type of attraction, and it's like magnets. It's kind of an opposites attract force of attraction, so it's stronger than a dispersion force that's temporary. Has to be polar, and this force of attraction, again, is stronger. There's a special type of dipole-dipole force called hydrogen bonding. It's not a true bond, even though it says hydrogen bonding. Very commonly known molecule water has hydrogen bonding. If you've ever belly flopped into a swimming pool in the summer, you have felt hydrogen bonds. You are breaking them. It hurts because water loves itself. It wants to be attached to itself really more than anything else. And it's because of this strong force of attraction, this special dipole-dipole force called hydrogen bonding. So if we were going to draw the Lewis structure of water, okay, water has two lone pairs on one side of its molecule. So what makes water special is not only is oxygen very electronegative compared to hydrogen, so it's a really big bully pulling on their shared electrons. Okay, that makes the oxygen side a little bit negative and the hydrogen side a little bit positive, but oxygen also has these lone pairs, and lone pairs are electrons. They're very negative. So hydrogen on another water molecule that already has a little bit of a positive charge loves that side of oxygen. So if I had another water molecule, these hydrogens love those lone pairs, okay? That attraction between the bonded hydrogen, the one that's attached to an oxygen in water, and the lone pair on oxygen is called a hydrogen bond. Oxygen's not the only thing that can hydrogen bond. There are other electronegative elements, fluorine and nitrogen, that if they have lone pairs on them and a bonded hydrogen in another polar molecule is attracted to it, that is also hydrogen bonding. Water is our most well-known example of hydrogen bonding. Along with DNA, the stair steps of DNA have hydrogen bonding. That's what is holding those stair steps together. One other thing we want to talk about with covalent bonds, just as a wrap-up, we've already drawn single bonds and double bonds and triple bonds, but one thing we didn't mention was that when there's multiple bonding happening, double and triple bonds, that is a lot of electrons in one area, and they don't like to be there. So extra space is needed when there's multiple bonds, like double and triple bonds, and that's where sigma and pi bonds come in. So sigma and pi bonds are just areas in space where electrons are shared in a covalent bond. So we're going to make just a little, chart just to kind of summarize what you're going to see in multiple bonds. So in a single bond, we have two pairs of electrons being shared. A single bond only has one sigma bond in it, one area of space where electrons are shared. Single bond is one sigma bond. Double bond has two pairs of electrons being shared. There's still a sigma bond, which is the initial point of attachment, but there's also another area in space where electrons are being shared, so we need something called a pi bond. So a double bond has one sigma bond and one pi bond. A triple bond still has one sigma bond, initial point of attachment, and it has two pi bonds because of the extra space needed for the extra bonds. Okay, so it's really easy if you know this combination, this pattern, then it's easy to tell how many sigma and pi bonds are in a molecule, as long as you can draw the Lewis structure and see the bonds that are there. Triple bonds are the strongest bonds, and they are the shortest bonds because they're strong, they pull the atoms very closely together, so it makes for the shortest bond. Single bonds are the weakest bond and the longest bond because those atoms aren't pulled as tightly together. So just as a quick little review to make sure you understand the sigma and pi bond combination, if we go back to our water molecule picture that we drew here. So here's water. Water has two single bonds, so I would say that water has two sigma bonds. Okay, something like oxygen oxygen has a double bond in it. So for oxygen, the molecule, I would say there is one sigma bond and one pi bond. So just as kind of a review to make sure that you understand how to apply sigma and pi bonds. All right, so let's talk a little bit about electronegativity and polarity. So this is a water molecule, And we know now that this side of water is a little bit negative, so that means partially negative, and this side is partially positive, and it's based on the electronegativity difference between oxygen and hydrogen, and also those very negative lone pairs that are on oxygen's side. Okay, there's a difference between a polar bond and a polar molecule. A polar bond, to be able to tell, you have to have an electronegativity table like the one pictured here in your notes. I would not ask you to memorize this table, but you do need to know how to use it to tell if a bond is actually polar or not. So to tell, there's a little section right here that tells you if a bond is ionic, pure covalent, or polar covalent. You look at the differences in the electronegativities of the atoms that are attached by that bond. So the scale is right here. If the electronegativity difference between them is greater than 1.7, that means that one of those elements is such a big bully, it actually stripped the electrons away from the other one, so that's an ionic bond. If it's less than 1.7, then it's considered polar covalent. Polar because they're not sharing equally. And then if their electronegativity difference is 0, it is the same element attached to the same element. And that is called a pure covalent bond, or nonpolar. So here's how this works. We're going to draw 3 compounds and look at the bonds that are in each one and figure out if that bond is ionic, polar covalent, or pure covalent. So we have water, sodium chloride, and hydrogen. Remember, hydrogen's part of Brinkelhoff, our diatomics. So in water, there's just a hydrogen-oxygen bond. There's 2 of them, but that's the bond that we're looking at between hydrogen and oxygen. Oxygen's electronegativity value is 3.5, and if I subtract hydrogen's, it's 2.1. That difference is 1.4. So that falls in the range of polar covalent because it's less than 1.7, but it's not equal to 0. So this bond between oxygen and hydrogen is polar covalent. Sodium chloride, I kind of already know because it's a metal, non-metal, that this is going to be an ionic bond, but here's why. Chlorine's electronegativity value is 3, and sodium's is 0.9. When I subtract them, that is a difference of 2.1, and that is greater than 1.7 from our little reference scale, so that is an ionic bond. Okay, and then finally hydrogen, bonded to hydrogen, it's the same thing bonded to the same thing, so it's 2.1, hydrogen's value, minus 2.1 is 0. So that's pure covalent, or non-polar. Okay, so that's just looking at a bond. To be able to tell if a molecule itself is polar, you have to be able to draw its Lewis structure, and that's going to give you big clues as to whether or not it's polar. And that's what the bottom of this page tells you. It says that to determine if a molecule is polar or not, the first thing we have to do is draw the Lewis dot structure. So I've got a couple of examples here that we'll do. CH3Cl, I'm going to draw its Lewis structure first by counting the valence electrons. So carbon is 4, hydrogen is 3, and chlorine is 7. So that gives me 14 total. Remember, the least electronegative atom goes in the middle, or if carbon is there, put carbon in the middle. I make single bonds to everything in the compound to start with. I've got 3 hydrogens and a chlorine, and remember, I want to keep those bonds as far apart as possible because they represent electrons and they want to be spread out. And then I make sure that everything has an octet in my appendages, all the things that are coming from that central atom, except for hydrogen. Remember, it's full when it has 2, or a duet. So carbon has 8, 2, 4, 6, 8. Chlorine has 8, 2, 4, 6, 8, and each hydrogen has 2, and I have 2, 4, 6, 8, 10, 12, 14 total. So my picture is done. So I did the first part. The second thing says if there are lone pairs on the central atom, the molecule is polar. Well, carbon is my central atom, and it does not have any lone pairs. So as of now, this is non-polar. So let's look at rule number 3, and we're going to rewrite it a little bit. If the central atom is bonded to atoms that are different. We're just rewriting that a little bit so it's not so confusing. Then the molecule is polar, and I can't spell different, apparently. Different. Okay. So let's look. Is carbon bonded to different things on each side? It is. There's a chlorine and 3 hydrogens. So this molecule is polar based on that second rule that we looked at. The other thing I want you to be able to tell me is, now that we know it's polar, I want you to be able to tell me what kind of intermolecular force of attraction would attract this molecule to another CH3Cl, another molecule like it. Well, now that I know it's polar, I can say the intermolecular forces. You always say dispersion forces because every covalent compound is at least attracted to another compound like it by dispersion forces because it has electrons. So dispersion. And then because this is polar, it also has that opposite charge attraction that polar molecules have, and we call that dipole-dipole force. Okay, so the intermolecular forces, because it's polar, are dispersion forces and dipole-dipole. Then the last thing I want you to tell me is how many sigma and pi bonds are in the molecule? Well, remember, every single bond is a sigma bond. So there are 4 sigma bonds in this particular diagram. By this particular molecule. All right, let's draw water and just kind of follow the same rules. Hydrogen has 2 and oxygen has 6, so 8 total electrons in water. Oxygen goes in the middle. Remember, when there's 2 lone pairs and 2 bonds, those lone pairs gang up on one side of the molecule because they get more space that way. Now, I need to decide if it's polar or not. So it does have lone pairs on the central atom, so water's polar. We already knew that. Forces of attraction are the same as our CH3Cl, dispersion, and dipole-dipole. And sigma and pi bonds, it has 2 sigma bonds because there's actually 2 single bonds, so 2 sigma bonds. All right, so that concludes our lesson on covalent compounds and how polarity works to determine intermolecular forces and how you can tell by drawing Lewis structures if a molecule is polar, or if you have to look at a bond using your electronegativity table to see what the difference in values are between the 2 atoms in the bond to tell if the bond itself is polar.